Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. But not just another Tuesday live stream, it's a CPU summer. This summer, we're highlighting the new modular controllers from Horner Automation, a new product category for us, and the first product released is the CPU250. Here's today's topic. Using the micro CPU250 with stepper motors. So there's so many good things you can do with this new product. Today, we're going to highlight interfacing with stepper motors. Now, if you missed the launch webinar, it's available on our YouTube channel. Basically, that covers the commercial information, pricing, that sort of thing. And last week, we covered hands-on, which is getting you started using Cscape 10 along with the CPUs, exercising the I/O, and all kinds of that good stuff. And today, we're focusing on integrating stepper motors with the new CPU. Without further ado, let's get started. Now, right out of the gate, I'm going to mention that we have a reference video for you folks who need a little more detail than what I'm going to provide today on stepper motors. In the reference video, we cover how does a stepper motor work, how does it compare to servos, etc. Today, we're really focused on the CPU250 and controlling steppers from that particular product. All right, let's go. We're going to start with a quick review of the CPU250, just hitting the highlights. We will spend a little bit of time talking about stepper motors, but most of the time we're going to talk about interfacing with stepper motors, whether you do it from a field bus or industrial Ethernet, whether you do it strictly from I/O signals like step and direction. We're going to show you the steps involved in controlling motion from the CPU250, and don't worry, there will be plenty of demonstrations. So here's a quick look at some of the hardware features of the CPU250. You can see them all covered here in detail. Now, we did take a look at these last week in our hands-on video, as well as the week before with our launch. Here are the hardware features and highlights for the CPU250. It's got all the peripherals you're used to seeing in the Micro series. You know, a built-in Ethernet port, a couple of serial ports, a CAN port for remote I/O expansion, but it also has local I/O expansion using OCS-I/O, up to 7 modules worth. And it supports all the same protocols you'll find in the Micro series. It also, from a CPU250 standpoint, has an amazing complement of built-in I/O, and those are highlighted here. But today, we're going to focus on the 2 high-speed DC outputs, which are capable of stepper control. Okay, let's spend a few minutes introducing stepper motors. What is a stepper motor? It's a type of brushless DC motor that's used for simple positioning applications. The way a stepper motor works is that a full motor rotation is always divided into a number of equal steps. It could be 200 steps per revolution, could be 400, could be thousands of steps per revolution. Depends on the motor, depends on the application. And steppers are known for their ability to position without requiring any kind of encoder feedback. So they work well in open loop. Now, what are the advantages of stepper motors? Well, they have a relatively low cost. Again, they do work well in an open loop type configuration. They're pretty easy to use, and they have great torque at 0 speed and at low speed. So you won't find them hunting around when they're resting, trying to hold position. They have great torque when they're not moving. Now, when would you use a stepper? Low cost applications, low speed applications, applications where you're moving from point to point, maybe going from point A to point B to point C, back to point A, that sort of thing. You get high continuous torque without the need of a gearbox. So how can you control a stepper motor from the CPU250? Well, you've got some options. Plenty of stepper motors support CAN open. They've got it built right in, and CAN open is an option for the CPU250. So that's a great approach. Another would be using Ethernet. You'll find some stepper motors with Ethernet built in, and many of them support Modbus TCP, also supported by the CPU250. But probably the most common interface you'll find on stepper motors is a pulse train style interface, which only requires I/O signals of a special type for control. And that's what we're going to be focused on today, using a pulse train interface to control a stepper motor. So how are we going to wire our CPU250 to a stepper motor that supports a pulse train or step and direction style interface? Well, let's start with the step or clock signal, which is the signal that tells the motor how many steps to move. That needs to come from one of the two high-speed outputs on the CPU250. So that's either Q1 or Q2. Now the stepper motor also requires a signal for direction, clockwise or counterclockwise, and in some cases it'll also need an enable signal. Now those can be wired to any output on the CPU250 because there are no high-speed requirements for those two signals. And then in addition to those three output signals, you're going to have common and 24-volt signals required as well. Okay, now we need to talk about what's called a trapezoidal move profile. This is the type of move profile that the stepper motor is going to execute. What does it consist of? Well, the stepper motor is going to see a pulse train that will cause it to start accelerating from a starting frequency up to a running frequency. It'll take a certain amount of time or a certain number of pulses to accelerate. Then it will get up to the running frequency where it'll stay for a certain number of pulses. Then as it approaches the destination, it will start decelerating back down to the starting frequency and then stop at the destination. So by specifying the parameters in the table on the left, the CPU250 is able to put out a pulse train, which will cause the stepper to execute the trapezoidal move profile on the right. Now let's give an example with some numbers. All right, let's say we need to move a total of 8,000 pulses. Okay, maybe that represents 40 revolutions, maybe it represents 5 revolutions of the motor. But anyway, we want to move 8,000 pulses. And we know we need to start with acceleration and end with deceleration. And let's say that we want 800 pulses of acceleration and 800 pulses of deceleration. Well, that means we need to run 6,400 pulses to get a total of 8,000 pulses. Now, what velocity do we want to run at? What number of pulses per second do we want to run at? Well, let's say that our max speed we want to run at for the move is 2,400 pulses per second. And we're going to start with a velocity of 800 pulses per second. That means during acceleration, we're going to have an average of 1,600 pulses per second, right? As you can see there on the chart. So how do we get these numbers to the CPU250 so those pulse trains can be generated? Well, we do that by putting those numbers in the appropriate I/O registers that are allocated for the stepper function. And you can see in the chart on the left, the next to last column shows the I/O references for stepper number 1. And if you're using stepper number 2, the I/O references are shown in the last column. So we load the appropriate values in the appropriate I/O registers to specify the move, and then kick off the move by turning on either Q1 for stepper number 1 or Q2 for stepper number 2. And we've also got some feedback bits we can use to make sure everything is working as it should. Now, here's a flow chart I've created that shows how the I/O should be changing as the move progresses. But instead of spending too much time going through the details of the flow chart, let's move right over to the Cscape demo program I've created and review it there. The first step in our logic program is we need to specify the move. So we need to specify the start frequency and the run frequency. These are both in pulses per second. So we're going to start at 1,000 pulses per second at the beginning of acceleration and the end of deceleration. And our full speed is going to be 10,000 pulses per second. All right. And then we also have to specify how many pulses we want to accelerate, how many pulses we want to decelerate, and in between, how many pulses we're going to be running at full speed. Okay. And all of these variables I've created are tied to the appropriate I/O registers in the program variable window. So let's go to the program variable window and see that these variables are all tied to the appropriate registers as per that table from our slides, and also, of course, as per the user's manual. All right, so we've prepared for the move by loading in these values. Next, we're going to go through a relatively simple process. First, we need to kick off the move by turning on Q1. And this particular variable is tied to Q1. In my case, I'm just turning it on through a push button, or actually it's a slide switch that's on my handy dandy I/O simulator. Next, we need to monitor the feedback bit to see that the motor has actually started moving. Okay, so our start move bit is on. We've turned it on. We wait for our move ready bit to turn off. That's that I30 bit if we're talking about stepper number 1. When that happens, we're creating a state in our program called move in progress. So that's how we know that the move has started, because this feedback bit has turned off. All right. Now, once our move is in progress, when that feedback bit turns back on again, we know that our move is complete. So we go ahead and say the move is complete. That's a new state. All right. We turn off the move in progress state. We turn off the start move command at the beginning. And then we'll be ready for another move to execute again by kicking it off again. In my case, by turning on this push button and doing the whole sequence over again. All right, let's take a look at it on the bench. All right, to demonstrate my move, I'm going to simulate the press of a momentary push button by sliding switch number 1 on and off, and that's kicking off the move. Okay, and I'm just repeating it here with multiple presses of the button. And of course, we can set up sequences with multiple moves in different positions. We can do all that just by adding logic to our CPU250. That does it for our topic for today. You've still got a couple of opportunities for OCS training during the 4th quarter, a basic course and an advanced course. Sign up on our website. Our trade show schedule is crazy in the 3rd quarter. We're going to be all over the Midwest and the South. Come check us out, see some new Horner products, and talk to us about your application. Lots of ways to interact with Horner Automation online, including our website, our YouTube channel, and on LinkedIn. All right, next week, the CPU summer continues as we're going to be showing you how to interface the micro CPU250 with variable frequency drives. It'll be a good practical session. You don't want to miss it. If you haven't done so already, don't hesitate to subscribe to our channel. It doesn't cost anything. And if you choose notifications when you subscribe, you'll be notified every time we go live or every time we post a new video. Okay, so until next week, let's all get out there and do some good.